This lab observes the motion of a slinky dropped from static equilibrium. This experiment examines the positions of both ends of a slinky with respect to time using two cases: observed measured position and model predicted position based on Hooke's law and Newton's second law. First off, there's the setup of the lab with its initial conditions before being dropped. Values such as mass and stiffness are listed for their effect on the duration of the slinky's practical levitation after being let go. Here is the footage of the slinky being dropped. It is detecting the positions of both ends of the slinky. As you can see, the bottom practically levitates while the top falls down. The point masses and compressions on the bottom aren't changed, and so the balance of forces they had while being held are maintained for a short period of about 0.3 seconds before getting the signal from the top that it's going down. This happens once the slinky collapses enough and the coils slam into each other. GlowScript can model this by making calculations based on Newton's second law and Hooke's law. Newton's second law explains how gravity acts on it, and Hooke's law explains how the springs work against gravity to prevent the bottom end from falling. Now, before seeing the model, know that it will not be able to completely replicate the event, but merely demonstrate the physics principle's utility in the phenomena. The values of the lab setup are mainly approximations and estimates. Also, due to the model operating on certain assumptions, it will not account for factors which could include the model's accuracy in predicting position. These factors include that the tracker's location marker is not always consistent with pinpointing the center of the object at a given time, and the drag force on the object could cause change in velocity, and the center of mass of Slinky as well as other points of mass aren't pinpointed. And so here is the model. As you can see, the bottom stays still until about 2.5 seconds, where the model representing the slinky is pretty compressed. Here's the code. So here I have my initial values based on the footage and approximations, and the model acts as if the slinky has certain masses connected to massless springs. The code stops at the point that the slinky would normally be slowing down. The process can be generally explained as there being two spring forces acting with both masses. Due to their being stretched and the direction with regards to the center of mass, their combination with gravity influences the levitation. And so here is showing more about where these forces act. So you see here we have the effect of gravity as well as the effect from the springs. And anyway, so in the model it's shown that the bottom end of the slinky doesn't start falling until the top end gets near it, and this occurs about 2.6 seconds in our case. So this represents when the coils in between the ends slam into each other and then the slinky is collapsed. So after this, both ends then start to accelerate downwards to gravity. And so anyway, I decided to use this as my lab because I thought it was pretty cool stuff, and it's an interesting way about how physics principles affect things. Anyway, that's all. Thanks for watching.